So the first talk of the second session this morning is to be given by Professor Chuan-Tsung Zhan Chuan-Tsung 教授 from Tunghai University. He's going to tell us about Li-Yang zeros of one-dimensional spin chain models. Let's welcome him.
First of all, maybe I should apologize for this very short presentation. I promise I'll be on time. And this work is in collaboration with my former students who graduated from our universities, but now he is in Tsinghua University doing his PhD, Wu Xuanyu, okay? And during this talk, there's only one thing which I think is new. The other maybe just some elementary material. Of course, most audience from condensed matter communities or statistical physics know this very well. But for other people, maybe it's worthwhile effort to at least see it again, okay? My own interest in research is about matrix models and integrable system, in particular, those aspects coming from orthogonal polynomial. That's part of the reason I start to investigate these questions or problems, okay? Also, the title is different, little different from the original post, because I realize many people prefer to use the word zero instead of roots. Well, anyway, it's equivalent. I'll focus on some basic results and only made comments about some observations during our studies. This is still an ongoing project. Also, I'm very sorry if I didn't make the citations or reference properly. Sorry, this is very, I only have very few times to prepare for this document. Okay, so in this half an hour talk, I hope to address the line of thinkings throughout these three steps. First of all, let me remind you, there is a beautiful connections, at least for certain class of integrable spin chain models, that there is a connections from transfer matrix to partition functions. Okay, I think this is also very useful either in designing or computing the physical quantities, okay? Secondly, maybe for those who don't know, let me just briefly introduce the idea of Li-Yang zero, which also connect back to the Fisher zero that the first speakers mentioned. Using the simplest examples, namely the one-dimensional Ising models. I think maybe all the audience in this room know that historically and physically, one-dimensional Ising model is the first example people try to address phase transitions using some mathematical analysis, but unfortunately this fails. But for me, instead of pursuing the directions of thermal transitions, I would like to see if there's other direction one could probe quantum phase transition, namely that study the phase structures in the parameter space. Okay, instead of tuning the temperatures. So throughout this talk, the temperature will be set at fixed value. And thirdly, this is what I mentioned, the new material I and Wu Xuanyu discovered. This is a new scaling law for this, at least for these particular models. We have a very precise plot and relations among coupling constant and magnetic fields. Oh, I'm sorry, the distribution of the Li-Yang zero. I'm sorry. So for me, this is the new result I hope to report in this workshop. Okay. Finally, I made some comments about some other things we explore during this study. Okay. So I hope the thought is clear. Okay. I'm sorry. I'm sorry again. Usually my style will be go ahead and doing some mathematical analysis. But I think this is much easier than the 6J symbols. So hope everyone has taken a course in freshman calculus could understand, okay? So I think everyone agree that no matter which theoretical physics you're pursuing, partition function is a very important object. And in the particular models of integrable systems, also for spin chains, there is a very useful connections based on some idea of transfer matrix. In particular, transfer matrix contains the essential information about partition functions. also their dimensions are usually very small as compared with the original configuration space. And in the case of one-dimensional system, usually by making this product of transfer matrix and taking the trace, you obtain the partition functions. And this is very popular formula in all kinds of systems. For me, I want to now define generating functions, promoting all finite systems into the so-called grand canonical partition function in physical terms. So this is the particular combination with auxiliary variable lambda now. In a later discussion, of course, physically, you can identify this as some exponential of chemical potential, okay? So for the moment, let me just do mathematical extrapolations from finite system partition functions and summing over all possible number of n, okay? And this is a very straightforward calculations. If you inject the structure of transfer matrix, this is simply a geometrical series, okay? So that function I define mathematically as generating function for finite n partition functions now can be written as this simple case where these are transfer matrix sitting here and lambda is these auxiliary variables, okay? As I just mentioned, if you replace this lambda with this form, then this is usually called grand canonical partition functions in statistical physics, okay? To make the connection into more useful forms, in particular, I want to make a kernel which once you know the transfer matrix for a particular system, you can immediately spell out what is the generating functions. Let me extract the eigenvalue information hidden in the transfer matrix in this way, okay? Everybody know when you are high schools, computing the determinant of this characteristic equation is important procedure to extracting eigenvalue of transfer matrix, right? So with that, now I can connect these Q functions with T matrix. That would be the next step. Okay, first of all, again, in linear algebra, there's an important formula. If you take the log of characteristic polynomial, then it is log of determinant, okay? And replacing these orders, you get trace of log. And furthermore, if you take the derivative on both sides with respect to lambda, you get back these connections, which is nothing but the generating function I just defined. Okay? So that tells you, if you want to understand the grand canonical partition functions in terms of chemical potential, you can easily first extract the characteristic polynomials from the transfer matrix and taking log and taking derivative. Okay? So that is the kernels starting from transfer matrix to grand canonical potential. That's the content for the first part I just mentioned. Any question? Okay? So 9 minutes. Now let me go to the concrete examples about to describe, which is the standard one-dimensional Ising models. Here, I have, in addition to the nearest neighbor, couplings with a uniform number J, I also add in this external constant magnetic field B, okay? And again, the partition function for finite number of spins is given by the sum of Boltzmann factors, okay? Oh, to make a mini advertisement, I also make an interesting observation of how to derive this Boltzmann distribution without resorting to Lagrange multiplier. If you're interested, you can look up my recent post. Okay, so by combining these two things, okay, everybody know that the partition function now will become a function in terms J and B, summing over all possible configurations. And also, as I mentioned, I'm interested more in the quantum phase transition, meaning the separation of different phases in the parameter space. So I fixed the temperatures in terms of J tilde and combining the external magnetic field with temperature into B tilde. Right. And of course, with this prescription, this is very easy. All the spins are either plus or minus ones. Using the computer programs, you can easily generate all possible finite n partition functions. And it is due to these Boltzmann factors. One can easily see that usually for finite n, this will be a Lorentz series in terms of exponential j tilde together with exponential b tilde. Okay, that's what I mean by polynomial in this sense. This is very similar like the terminology in knot theories. Even you have negative power, you call it polynomial. Okay. For the definition, any questions? Oh, good. Good question. For this talk, I just simply consider closed loop. Yeah, periodic. You can, of course, also extend this study to open chains, which amounts to insert a twist operator inside the closed chains. You just flip two adjacent spins. Okay. Okay, for that standard Ising model, the transfer matrix is given in this way, and then you can compute the trace and determinant. Hence, the characteristic polynomial is a quadratic, because as I mentioned in the very beginning, usually the dimension of transfer matrix is much smaller than the dimension of the whole configuration. Okay, so using that and the formula I just discussed before, from the characteristic polynomial, you can extract the grand canonical partition function, which in this case is a rational function in lambda. Okay, and then if you want to project out a particular partition function, you simply do these residue calculations up to a certain order. And this formula will also help for if you want to just study the asymptotic behavior without knowing the exact formula, because I think everybody knows that by projecting up certain powers of poles, you get the finite partition function Zn. Okay, and if you look at this expression closely, but actually you don't, you don't need. You'll see that this is nothing but the generating function of Chebyshev polynomials. Okay, actually, well, in a standard textbook, normally after these steps, we simply solve the eigenvalue exactly, and there are only two eigenvalues. The partition function will be the sum of nth power of two eigenvalues, right? So at that stage, already you will see that this is a Chebyshev polynomials without resorting to this formula I just derived in the first part. But this is more useful if you consider more complicated models. Okay? So that's why I use this page to illustrate the idea of first sections. Any question? So the second point, just to make the name more precise, as I said, I'm very interested in orthogonal polynomials. So this is after a suitable adjustment. The partition function of finite n periodic one-dimensional Ising model is precisely given in this form. This Tn is the nth order first kind Chebyshev polynomials. Okay. And the external field dependence will hidden in the trace and determinant. This is the overall factors. Now, by Li Yang zero, this was already discovered in their early career, even before CP violations. Oh, by the way, the reason I touch upon this subject also has to do with some invitation of writing some general science promotion articles in Science Monthlies. At that time, I thought too many people has written down on the CP violation contribution by Li Yang, and I thought I cannot do better than that. So I pick out some special topics I feel interested, which is the Li Yang zero. That's how I get into this business. By Li Yang zero, we mean we ask for when the partition function will vanish. This is because even though I mentioned in the beginning, partition function is the core object in the study of theoretical physics, but usually in order to extract physical observable, you need to take derivative. In particular, the free energy, the derivative of free energy, which is log of z. So naturally, if you write all the physical observable in terms of partition functions, they'll go downstairs as a denominator. And in particular, if you want to study the phase transitions, which diverge at some particular parameters or temperatures, then which happens at the 0 at the z. So that's why Li and Yang try to investigate a scenario or a criterion to judge when the system will have phase transitions. And that's the motivation for studying the 0 of partition functions. And because, as I just emphasized, this is a Chebyshev polynomials, the 0 is precisely known. Okay. Unlike the two-dimensional case, I don't think there's a precise formula for this or the root. Okay, so this is the zeros of Chebyshev polynomial in this way. Xk will make this if you consider this polynomial as a function of x, this Xk will be the roots or zeros, okay, and which are precisely given by the partition of the circumfield. And with that, I can translate to the roots of partition functions because there's some overall scaling, things like that. And this is the precise results. And that will establish connection between the external field B and spin coupling J. There will be an implicit function dependence due to the requirement I'm studying the 0 of partition functions. So this is the title, Li-Yang 0, at least for one-dimensional easy model with periodic boundary conditions. Is that okay? So H here stands for the magnetic field. J is the coupling. Okay? And as you can see that even though there's an implicit relation, you can very easy to shift this to here and get explicit dependence of magnetic field to the spin coupling constant. Okay? Any questions so far? In particular, if you consider the strong coupling where the J goes to infinities and sinh is almost like an exponential. Okay? So this will cancel. And from this equation alone, you'll see that at the strong coupling limit, the Li-Yang 0 for magnetic fields is evenly distributed along the circle. Okay. Which can be seen in the following diagrams, I think. So yeah. So this is a plot of H when the J is equal to 4. Okay. So I consider n equal to 12, but I include both branch. It's a complex conjugations. In principle, for this, maybe up half is enough. Okay. So it's very evenly distributed when the coupling is very large. On the other hand, if the coupling is very small, you'll see the Li-Yang 0 accumulate near the North Pole or South Pole. Okay. So at first I was very excited. I thought, oh wow, this might be a phase transition. That's part of the excitement we have. But I want to characterize this difference of this different distribution behavior. So the first thing is that we should identify a proper order parameters, right, in order to describe the distribution of the zeros. So that's the new thing we come in. How much time do I have now? Okay, good. That will be sufficient. So my collaborator, Xuanyu, who worked very hard, I asked about whether he can imagine some good order parameter to characterize these distributions. And this is the answer coming out. Okay. So phi is the angle of these magnetic fields. Oh, by the way, since in these particular systems, the magnetic field is precisely imaginary number. Okay. And according to the criterion of Yang and Li, the distribution either in this I'll call this Cartesian, and this is like a spherical or polar representations. The accumulation of the Z-Yang 0, if in the larger limit, path through the real axis at non-zero point, that will have non-trivial phase transition. But in this case, since this is purely imaginary, it passes through origins. So that's why in this system, there's no phase transitions. Okay. Li-Yang mentioned this in their original papers. Okay, so this is the criterion that Xuanyu proposed. Okay, actually, this is two angles. So before you see that in the diagrams, when the coupling constant is very small, it accumulates to 90 degrees or minus 90 degrees. So by taking double angle, it will goes to this direction, right? And that's how he imagined to define these order parameters. Okay, we want to see if this number is very close to +1, because this is 1 divided by minus. Okay, that's the original idea. And after I see this, I think, oh, good. Actually, I think we can make some more precise manipulations. For him, it starts as a ansatz, okay? But due to the simplicity of these models, one can actually prove some things. I'll not go through the proof in the following 10 minutes because I promise I'll keep time. But let me show you, after we identify these order parameters and making a plot, what do we get? This is the plot, okay? So in the horizontal axis, I have the strength of spin-spin interactions. In the horizontal axis, that is the order parameter capital N with finite n, I just defined, which is cosine 2 phi k. And this is very beautiful, right? By the way, this is for different, sorry, n is fixed, but changing the strength of spin couplings. Everybody see this will first response, oh, this must be an exponential, right? And indeed, if you take the log plot, it's a straight line with a good feat of slope, which is -4. Okay? So indeed, we can prove that. I think I skip this because I don't have much time. So starting from these definitions, this is a definition for characterizing the distribution of Lie zeros. After some simple algebras, we can prove that this is nothing but this. Okay? So that explains the curve we just observed. Okay? It's indeed an exponential with, if you plot in log scale, it's -4 slope, straight line. But what is even better is that now we try to modify and generalize these studies to next to nearest neighbor couplings with additional coupling constant, like let's call the nearest neighbor J1, J2, and J3, J4, and so on and so forth. Okay, but each are pairwise interactions. We also found this. This is a contour plot with two coupling constants. This is the nearest neighbor. This is next to nearest neighbor. So this is J1, J2. And we plot the contour plot of these order parameters. And this is 45-degree diagonal. Okay. And for the moment, I don't have a direct proof. If somebody can help, that would be nice. So we conjecture the following fact according to the observations. That for the standard one-dimensional Ising model, this is precise and can be proved exactly. But for general system, the order parameters with log will equal to the sum of all the couplings. Okay, but at this level, this is just a conjecture and numerical observations. Okay, so the other observation we have made is to study more extended spin system, but still 1D, including maybe triple spin couplings and so on and so forth. But usually, 5 minutes left, right? Okay. Usually, we don't have such beautiful pictures. The circle theorem is not necessarily guaranteed. Okay. In some case, there is zero we are wandering around, and I'm still trying to figure out what is the general patterns if I can make it more precise. Okay. So that's all for my report. Thank you very much.
This end of Einstein, the distribution from the answer.
Oh, okay, but I can only answer in words. I don't have transparency here. Usually, when you plot this, this is with respect to this. This is small. H is the magnetic field. So that's why if H is pure imaginary, magnetic field, the B, okay? So if I use this variable, then they should lie on the unit circle. But if I plot the diagram directly using H as variable, I should see a straight line on the pure imaginary axis, right? It's just I times real number. So if I plot H, that would be a straight line. It's just a matter of representations, okay? So the statement about phase transition is that if I study either this accumulation of H or Z, for Z, if they don't lie on the, if H, the accumulation for large N pass through, it doesn't have to be a straight line. In some simple example, for example, you can check Wikipedia. There's even more simpler models. If the accumulation line of H, for example, passing through a non-zero point, then there's a non-trivial phase transition. But in this case, for a one-dimensional easy model, the H pass through origin. So there is no non-trivial phase transition. I mean, at least thermally. The thermal phase transition only appear at t equal to infinity or 0, I remember, because it passed origin. Only when it passed through non-zero number, it could have a non-finite temperature phase transition. Right. You consider now it's a right. Real number. Oh, as I also mentioned that because all the physical observable coming from the derivative of free energies. Free energy is log of z. So in particular, many observable will have z in the denominator. When z becomes 0, it diverges. So that's why Li-Yang 0 is a detection of existence of phase transitions when the physical quantity blow up. Yes. I mean, typically for finite system, you only see a peak instead of a pole or divergence. Do I answer your question? Okay.
Are there other questions? So you had in the last result sum over J A.
Yes.
So K is only 1 and 2, right? You can
No. It could be arbitrary. We try many
Arbitrary.
examples.
I see. So you
Which
expect,
means you have nearest neighbor coupling, next to nearest coupling.
and then next. I see. All the way is this is.
It could be infinity. I mean, in principle, I don't.
Okay.
But the thing is that this has to be a pairwise interactions.
Okay.
Only
On both sides.
only coupling between two spins.
Okay.
We also study the so-called three-spin couplings, which means in the Hamiltonian you have J1 times JK times JK plus 1 times JK plus 2. That's what we call three. But in that generalized systems, in general, the 0 will not lie within on the circles. It can fluctuate things. I don't have good patterns yet.
Thank you.
The interaction in the infinite.
Right. You are referring to the statement by Thales, I think. Thales also made a study for long-range interactions. I think the critical case is 1 over r squared or something like that.
So for the right-hand side doesn't depend on things that.
Oh, I'm sorry. This case, label for different types of interactions. Yes. Yes. You mean the Okay, maybe I should make too strong statement. Maybe if K goes large, there's something different happens. I don't know yet. But for the moment, I only try maybe up to 5. Like 12 or 20 in computer calculations. Yeah, I agree with you. Maybe if I include a very long range interaction, the scenario will be changed. I don't know that yet. Not yet. Not yet. I'm sorry. I hope so, but I don't know. Yeah. We're still pursuing this.
Okay, let's thank Chuan-Tsung again for a very interesting talk.